Hi, my name is Michael Herndon, and today I'll be presenting my lab analysis for Lab 1, Constant Velocity. This lab focuses on analyzing the motion of an object moving at a constant speed and in a straight line without changing direction. Using Tracker and GlowScript, I recorded the object's motion, extracted the necessary data, and compared it with the computational model based on Newton's second law of motion. The purpose of this lab is to demonstrate our understanding of constant velocity motion and Newton's second law, which states that an object will retain in constant motion unless acted upon by a net external force. Additionally, we will verify our computational model by comparing it with real-world observations. So to continue on with Newton's second law, just to say it in different words, if I was to apply force to an object, the greater the force, the greater the acceleration. And for the same force, a more massive object will experience less acceleration because it requires more force to change its motion. Here is the tracker software that we used. So for setting it up, I had to set my X and Y values, as well as use a calibration stick to set the length. And as I play the video, in our bottom right, you can see our time, as well as our position on the X-axis and the Y-axis. I will not be focusing on the y-axis because as you can see through the video, our y doesn't actually really change. I will, however, be focusing on the x-axis because that's what will be changing throughout the video. So for our computational model, here's our starter code, and the main variables I wanted to focus on was our mass, our velocity, as well as our time. So I need to find the velocity of the object and the time in order to update our position of the ball. And then the bottom right here is the average velocity formula, which is our change in position or displacement divided by our change in time. And where could we find this? We could find this, as you can see on the bottom right, this is zoomed in. We could find all of this here. We could find our final time as well as our final position to get us our initial or average velocity. So with the values updated, our mass is 0.1 kilograms, our velocity is 0.646, and our delta t and time, delta t being 0.033 to follow the time steps that were used in Tracker, and our time being 1.3 to follow again Tracker. That's how long it took to get across the distance. Down here, we have our ball velocity equals ball velocity plus vector of 0. This is right because our velocity actually never changes. There is no net force acting on it. So our ball velocity will remain 0.646 throughout our entire loop. However, our position will be updated by our velocity times the change in time to get our updated position. And if we were to run said code, we are able to get this graph. We're able to get this graph here, which plots our position versus time, and as you can see, it's a linear line, which matches our velocity not changing theory. So here I applied both the observed position versus time and the predicted position versus time. The comparison showed that the model successfully predicted the motion of the sports tape when the net force was 0. This is consistent with what we expect in the case of an object moving at constant velocity, the absence of any unbalanced forces. So to obtain good agreement between the model and the observations, some assumptions did have to be made. We assumed that external forces such as friction and air resistance were negligible or perfectly balanced by other forces, leading to a net force of 0. This allows the object to move at a constant speed, which matched the behavior observed in the real world. So, what if we change the orientation of the axis in Tracker? If we flip the axes, meaning the positive x and negative x directions were interchanged, the motion would still look the same in terms of its speed and straight line path. However, the sign of the position values would be reversed, as so. The overall conclusions about constant velocity would remain unchanged since flipping the axes doesn't affect the physics of the object's motion. So, what does it mean? Addressing the question of how many forces were acting on the object, I don't think it's possible for us to figure out how many exactly distinct forces were acting on the object. However, we do know that this was added to give 0. Yeah, like just purely based off the eyes, no, I don't think it's possible. But we can get a good guess of what the sum is, which is 0. And that's all. Thank you all for watching.